Welcome everyone to this live session on process control design and analysis and assessment NPTEL course. So we have looked at various methods of designing control for CISO systems in this course. We started from defining what control is, and then we had an in-depth view of CISO system control, what are the elements of CISO systems control, and various methods. So this session is meant for clearing any doubts you have and any other questions you have that needs further analysis or something. We haven't got any offline questions posted by you guys. With respect to online forum, what we have found were already answered most of the time. A couple of questions which we have not yet answered is like how we get FIR model coefficients. So I'll start by saying how we get the FIR coefficients so that that is clear. Since control is more or less discrete, so we don't control the system continuously because the control is based on computer. So computer outputs go at a certain fixed frequency, whereas the process by itself is continuous. And because the process is continuous, the model we develop, if we develop it based on first principles and other auxiliary equations, will be continuous continuous time framework. So we just convert that into a discrete domain by using inputs which are approximated as sum of impulse responses. The magnitude of the impulse response will change, but the nature of the input is kept constant between subsequent time instance in sampling instances. So based on that, we have the FIR coefficients. So Grace has asked a question. Give clarity on questions 7, 8, and 9 from assignment 10. I'll just quickly open that assignment so that I have a backup. No, no, that's okay. So, yeah, we have a couple of more questions. So, one question asks about when they can take the course again. So, this is already the final week of the course. The students who have registered are going to write the exam this weekend. So, maybe next semester this will be opened again. Please stay tuned. You can take the course again. So, with respect to the question 7, 8, and 9 of assignment 10, so yeah, so the uh, thing is, you have to compute the FIR coefficients as given in the video. So the system parameters A, B, C are given in the question itself. So how the answer is arrived can be looked at in the solution we have posted. So I hope you have seen the solutions. Uh, what you have to do is you have to set up the MPC with P equal to 5, M equal to 2, and Y set point equal to 18, and perform one iteration of MPC calculation for question number 7. Question number 8 asks for objective function. So the objective function you have to use is y minus y set point whole square, so sum of y minus y set point whole square, and sum of u whole square. So, sorry, sum of u square. Based on that, the answers are derived. But the question number 8 answer was found to be not in a little bit different than the options given. So we haven't evaluated question 8. So please keep note of that. And the question 9 is when you change the control horizon M as 1. So if you change the control horizon as 1, and then perform the same MPC calculation for one iteration, you will get that solution. That is also clearly derived in the solution posted. Yeah, and assignment 2, let me look at it. Can you clarify which question are we talking about in assignment 2? Because the chat message says you are getting option 3, but the correct option is 2. Yeah, so Mr. Pavan Krishna has asked about controller performance assessment. So, as far as I know, we are recording the lectures now. So that will be posted if there is additional uh, NPTEL course which is taken by professor. So the other way is otherwise we can request NPTEL people to give access to you guys also who have registered for this course. So yeah. Okay, so a couple of general questions. I have looked at the assignment for question 2. Um, yeah. The third option seems to be correct. So we'll reevaluate this assignment 4. Yeah. So Mr. Saravanakumar has asked whether the questions are going to be completely numerical and it can be solved within 3 hours. So we have made sure that it is balanced with both numerical and both simple application of whatever knowledge you have gained and with simple manipulations. So we haven't solved by ourselves for 3 hours, but uh, we have uh, faith that you can do it because at least for us it takes a little bit lesser than 3 hours. So it's always complicated to answer such questions. Now, Grace has asked another question in Cascade Controller, which one is the primary loop and which one is the inner or outer loop. So the innermost loop of the Cascade Controller is always primary because that drives the input to the process, whereas the secondary controller or the outer controller will be called secondary. I hope you can see it. What I'm talking about is that we have two sequential controllers. One controller controlling one part of the process and giving set point to the other controller. So that controller is called secondary controller, and the innermost controller is called primary controller. The other way. So yeah, so the other question is, yeah. So just
can you share this? Please?
Yeah, just we'll share that. Just give me.
Okay, you can put it like this.
No, just give the link. So now you guys can see here. So the primary controller gives set point to the secondary controller. So that is called inner loop, and the outermost is primary.
So,
it's the other way around, which I said. So the outer controller is primary controller, which drives the secondary controller. So it's master and slave controller. They are also called master and slave controller. So the innermost is secondary controller.
So one way you can think about it is like if you see the action of the NPTEL control loop, the main objective of keeping the set point at the set temperature is taken care of by the primary controller, and it in turn manipulates the secondary controller to achieve the main objective of keeping the outer temperature as set point. So it's like the main boss or something which is actually doing the task that is destined for the control loop.
So, MPC, no, as long as the problem of MPC solving is unconstrained, or you have constraints which are equality constraints, the MPC programs can be solved by hand. So the question number 7 to 9 of assignment 10, you can actually solve by hand also, because I have given only control horizon of 2 and 1, which implies you have only one decision variable or two decision variable in reverse order. So if control horizon is 2, you have two decision variable for CISO system. If control horizon is 1, and you have one decision variable for control horizon 1. So because of that, you can actually solve in pen and paper. Or if we have equality constraints, which is all the number of equality constraints are equal to the number of decision variables, then you can just solve these equations and get the solution, because the feasible solution will be only one, which you will get as a unique solution of the equality constraints. Only when you have inequality constraints and you have more number of decision variables than equal number of equality constraints, then you have to look at solving using optimization. So one question was why Nyquist plot, if there is a delay term, it encircles the origin infinite number of times. That is because if we assume the e power minus tau ds as infinite sum, we'll end up, or we can actually do third order, fourth order kind of Pade approximation. That implies you have infinite number of poles in the system, irrespective of the order of the system. Because of that, there is a encirclement around the origin infinite times.
So basically, if you want to mathematically show it, you can expand the e power minus ds term, like in the exponential expansion, like you have an expansion for the exponential series, and if you expand that, you'll get infinite poles. That's what the idea is. So that is the reason why you cannot use other ideas like taking the denominator, characteristic polynomial, and then checking the possibility, etc. That's where you go for these kind of systems to Nyquist plot. I think if you like, this was actually explained by Professor also in his lecture. You can also have a look at it.
Yeah.
And okay, and how to enroll in other courses? Like if you mean the next NPTEL course on process control, like you may be probably getting a notification from NPTEL people
in future.
So that's how.
So yeah. So with respect to the question regarding Cascade Controller in the assignment 8, whatever we have worked out is based on how we specified. So we'll clarify the specification and we'll change with the secondary and primary correspondingly. Sorry if it was confusing for you guys. And why
body plot fails sometimes? I think this we already looked into the lecture. Basically, like the body, the idea behind body is that if based on a Barkhousens criterion, which says that when at the phase lag of minus 360 degree, which is like with the negative sign, it's minus 180 degree. The gain is equal to 1, then the system becomes like unstable. But the thing is like it has a lot of assumptions in it. Basically, it kind of one thing you can say is like it assumes that the gain is always a decreasing gain. It is not. It cannot increase after a while, and the phase is also a decaying phase. So these details we didn't touch upon in the lecture, just not to like introduce you to lot of concepts in the short lecture, but still like it works most of the time, but it doesn't work sometimes because when you can see like gain is increasing in the transfer function, or like the phase is increasing in transfer function, so that's somewhere you can suspect that it won't work properly. But anyway, you can basically go and read books or the websites on body plot. You will get information about it.
Yeah, so the Smith predictor is used for systems with time delay. So Grace has asked this question. So I didn't get what she is asking. So if the question is whether it is used for systems with or without time delay, it is used for systems with time delay. And the ability of Smith predictor is that it doesn't require you to compute future input moves or future input profiles while implementing a controller. So you are essentially going to use past data of input and past data of output to control the system. So that is the use of Smith predictor. So because of that, it is used for systems with time delay. I hope it clarifies your doubt. Another question regarding NPTEL. So these courses are free, but if you need a certificate, you need to pay a fee and write an exam, which is going to be conducted in across various locations in India. So somebody has asked again the computation of inverse of a matrix. So that you have to do by hand only. So because of that, we won't give you any complicated like 4x4 system or 5x5 systems like that. So only which you can compute by hand will be given in the exam. So if it is a 2x2, you have simple formula to compute inverse.
So I think it's some time you have to go and look back at your math syllabus.
Assignment 10 solution has been given. So what exactly is your doubt? If you can clarify, then we can actually give more input on it. Otherwise, uh, so it's just the formulation of a standard MPC and then solving it. So what you have to do is, or I'll explain by showing you the solution. Maybe that will help you. Yeah. So the questions from 4 to 7 are related and they are applicable for a single system. So what I want you guys to understand is that it's not a single question. It is a series of connected questions. So the question number 4 asks for computation of impulse response coefficient at lag 3, and question number 5 asks for step response coefficient computation with respect to lag 3. So here, if you see, the prediction horizon of 5 implies you have to you are predicting 5 output variables in future. So given y of k, you are predicting y of k plus 1 up to y of k plus 5. So those has been given in written in terms of the coefficients which you are you have already calculated, which is like h1 to h8. Now notice, because we have control horizon of 2, we have two decision variables. They are uk and uk plus 1. So after, when your prediction, when the prediction horizon is greater than the control horizon, we need to write any k which is greater than 2, sorry, any k plus I greater than 2, we write it as in terms of uk plus 1. So we say u of k plus 2 is uk plus 1, and u of k plus 3 is also uk plus 1. U of k plus 4 is also uk plus 1. So because of that, yk plus 3 is given as h1 plus h2 times u of k plus 1, because that will be h1 times u of k plus 2, which is u of k plus 1, and h2 times u of k plus 1. So because of that, you have h1 plus h2 here. Similarly, h1 plus h2 plus h3, h1 plus h2 plus h3 up to h4 here. Now, what you have to recognize is that only uk and uk plus 1 are the unknowns. The rest are knowns. uk minus 1 up to uk minus 7 are knowns. So what I have done here is I reformulated the whole set of equations in terms of uk, uk plus 1 and known variables, which is a stack of up, which I have uk minus 1 up to uk minus 7. Why I have written like this is because it is easy for you guys to understand how it varies with respect to change in control horizon. Then what you have to do is you have to solve this optimization. So you have s times u plus t times up. So this t times up will be a constant. Ysp is given as 18. So you can actually compute this square and then solve. Or if you know the unconstrained optimal solution for this, it will be like a transpose ax equal to b kind of situation, where your a will be s plus identity of u, which is equal to uh, t minus t times up plus ysp whole square. So based on, sorry, ysp. So based on that, you will solve ax equal to b and then get the solution. The corresponding objective function, which is like sum of y minus ysp whole square plus u transpose u, is your objective function, which is computed in this. And when you change the control horizon from 2 to 1, you will not have this column because it will be UK plus 1, but you will have the whole column changed as H1, H1 plus H2, H1 plus H3, all the way up to H1 plus H1, H2 plus H3 plus H4 plus H5, and a single variable UK, and the rest similar T times UP. So based on this, you can actually compute the solution and you will get this solution, which is 0.906 or 0.91. So that was the answer. Hope this clarifies. Can you guys see the presentation or the solution? Yeah.
So the next question is, how do we approximate higher order systems into first order plus dead time? So if you could see in one of the tutorial lectures, we had done this approximation. Basically, what we have done is we have taken the maximum slope and then found that intercept as dead time, and then we saw like what time it takes from that point to reach 63.2% of the final value. That is the time constant, and the steady state gain is given by the final value of output to the final value of output by the input. There are other delta y by delta u. That is like gain. So I think this is in the lecture of PID tuning. So if you can go back to PID tuning, you can actually see that in the tutorial we have taken a quick example and that.
Yeah.
And there are a lot of variations to it. I mean, there are a lot of different methods by which you can achieve this. This is one method. So the idea of how to use the data itself to get the data instance, how this looking at the system response and seeing what is the transfer function, that itself is a separate course by itself. It's called system identification. So, but still, this will give you a very small introduction to the, so that you can look at the lecture on PID tuning.
Yeah, so the next question asks about how to solve assignment 8, question number 5. So the t value is the coefficient of s in the unstable pole. So I'll share the screen again so that you guys can see. Yeah. So what we have is two equations. These two equations where only tau and tau c are known. We have to compute uh, 3 more variables with 2 equations. Because of that, we have to assume one variable. So what I have assumed is the tau c and tau 3 are assumed, and that is given in the question itself. You have tau 3 equal to 0.1 and tau c equal to 0.1. The tau which we are talking about here is the coefficient of s in the unstable pole, which is 1 here. I hope this clarifies your doubt. So if it is something like 0.5s plus 0.5s minus 1, then tau will be 0.5. Go back to the unstable systems controller video, where you will say you will cancel out a pole and 0, which where the 0 will be the inverse of the system model. Because of that, whatever coefficient you have for s, will have to be same as the coefficient you will get from this tau 2 tau 3 by tau c. So that is tau is the coefficient of S in the unstable pool.
So anyone else has any questions? Like any more questions? Stop sharing. Okay, then we'll stay online for another 5 minutes. So if anyone has any questions, please post it. If not, like, okay, we got a question. What is the steady state gain? Question 1 is.
So yeah, so the steady state gains are the final value of the system model. So you just put S equal to, we have the final value theorem, right? So you have limit S tends to, limit T tends to infinity, F of T is limit S tends to 0, S into F of S into, S into G of S into U of S. Assume U of S to be unit step and then compute the gains. So the results, that is the options given in the solutions are not updated. So we have changed the options in the assignment. So yeah, so the SI minus so the SI minus A whole inverse times B converts your state space model to transfer function model. So if the model is in state space form, you have to solve the state space form in terms of integration and then form the solution. If we convert it into a state space, transfer function form, we can actually use final value theorem to compute steady state. So that is the idea here. So because this is actually two different equations, you have to simultaneously solve them. It will be a complicated solution for both values. Instead, we can easily compute it in terms of transfer function equations.
Okay, so to tell about that again, like SI minus A the whole inverse B cannot be a steady state gain just because it has the S term. So a steady state gain is a value; it does not have any of the Laplace terms. Just remember that.
And one more thing to remember is you have B term, which may consist of S along with uh, regular input values, constants. So the gains are not B matrix. The gains are the final value of Si minus whole inverse times B. So you have to compute Si minus whole inverse B, Si minus A whole inverse times B, and then compute the final value theorem. The approximation of higher order transfer function to first order processes are Parameshwaran, who is the TA sitting beside me, he told you. So there are a lot of methods, number of methods available for such approximation. So you can actually take the data and do the modeling again, and then approximate it as a first order process. But those are very case specific, and that need a little bit more careful analysis of the data and the system in question.
So one more thing to add is if you have a transfer function, just with the transfer function can you get a first order process? To that question, I'm not sure if you can actually do it. But what we can do is we have to simulate and get the data and derive the model from the data. Basically, you have a process. You have to give a step input to the process in the manipulated variable, and then you have to see the response. And with this input output pair with the data, you have a lot of methods for doing such approximations. Yeah. You can even get a state space model out of it. You can get a transfer function out of it. You can get different types of transfer function. First order plus delta time is one type. Second order plus delta time is another type. There are a lot of types of it, and there is a big course on it. There's a complete course on it called system identification. So if you are interested to know more about this, then I suggest that you take a system identification course, and I also believe that a course on system identification is already present on NPTEL, so you can just look into it. Regarding integral windup, it is a problem with PID controller. Basically, like this problem was most prevalent when you have this pneumatic kind of controllers which has no big smartness in them, and that there needs to be some mechanism to address it. So basically what it means, like you have an integral term and your process is very slow and your integral gain is high, it keeps on integrating so that it goes on integrating to some level that basically to come back to the operating region of the controller itself, it will take a lot of time. So that's the idea of integral windup. So basically, integral windup will occur when you have a high integral gain and a slow process. That's what you can think.
The question regarding assignment 9, let me look at the question. I'll look at the actual solution because the version which we have posted, it seems to be older. So I'll look at the actual solution derived and then I'll get back to you later. We agree that controller performance assessment is required. So the problem was like the portions were quite large. The areas covered were also in terms of methods, in terms of variety of processes which we have seen. We have looked at Nyquist stability criteria, etc. So all of these require a lot of deliberation, and the course length was also fixed for 12 weeks. So we had to cut off that portion of this course. So we'll try and upload the videos and give access to you through NPTEL or some other means. Please stay tuned. We'll do that.
We'll also try to get you some book references for it as soon as possible. So we know there's a book coming up, which is written by Professor himself. So
yeah.
So if that is it, I think we can.
Okay. So any of you guys further have questions, post here fast, because we have last 10 minutes here. So one question which I want to give more input on is that the higher order approximation of higher order transfer function. So a few points to remember is that if you approximate a higher order system to lower order, you may end up with model mismatch which cannot be controlled within the controller. So remember, we had inverse response problems and unstable control problems and time delay problems where we specifically used model of the system instead of the process itself. So you can actually approximate the higher order system to lower order. But the problem is if there are unstable poles or there is some inverse response, then you have to look at the robustness of your controller which you are designing. So because of that, in general, it is not. Uh, it's not an easy job to approximate it as a first order process. Also, it's also it will also introduce error into the controller calculation. So because of that, we generally avoid it. If you want to do it for some other reason, the method is to simulate the system using any persistently exciting input like PRBS or step response or sinusoidal response. Give the system sinusoidal input and then take data, and based on data you can fit the parameters tau, k, etc. But keep in mind, approximating higher order into first order system will introduce error, and that will reflect in your controller design. You cannot design the controller for process transfer function and try to use it for approximate model as a system. So those kind of mismatch also can happen. So you have to do the robustness analysis before approximating and designing controller. Hope this helps.
So basically, I think what he is telling is you cannot take a wrong transfer function and then put it and expect the controller to work fine.
Yeah.
You have to use you have to be as close as possible to the truth of the model. We know all models are wrong, but we try to minimize between the truth and
error. So the idea is even the transfer function model which we get is based on certain assumptions. So we either use first principles model to derive the first principles method to derive the model, or we use data-based modeling. If we use data-based modeling, we approximate all the nonlinearities into some error. So these kind of approximations will be introducing more error into your system or controller design if you are further approximating it into your first order process. So that's the idea.
Okay, I think then we are close to closing the session. We hope you all enjoyed the NPTEL lectures and hope that you got some, I think, good insight into what is different strategies of control. Like control itself is a big ocean. Like there are a lot of courses you can take after this. So this is like a undergraduate level course. So we also suggest that the fun with control is like when you start playing with it, when you start implementing it on system, when you actually put your control system on a tank and see if the tank is getting controlled or not. So we encourage you all to play around and get yourself familiarized and have fun with control systems. And yeah, that's what.
You can use Simulink to actually simulate the response, look at the robustness of the controller, etc. So we have given demonstrations on tutorials. So we hope that also give you an insight into how to work MATLAB. So you have 1 week of license, I think. So make use of it as much as possible. And we hope you get a good insight into insight and introduction into the process control, particularly design aspect and analysis aspect of it. The assessment aspect will be posted later, so we'll keep in touch with you. We'll give notifications as and when it is ready.
Thank you.
So yeah. We'll be here for a few more minutes, 2-3 minutes. So because it's we have been told it is till 12 o'clock. So any questions you have, you can ask us now.
So final slot.
Yes. We also request you to give feedback on how the exam is so that we can actually tune our own question papers in the future, because if you guys are feeling it to be very hard, please let us know. We'll change the question paper pattern in the next. So let me take a feedback on that so that we'll improve our evaluation methods.
So, but if you want, if you have some grudge against your juniors, you can also say it was so easy, so you can make it tough. And yeah, like, okay, exams are part of the course, everything, but more than exams and more than your the scores, etc., the concepts you learn, the new ideas you get from the scores, that's what is going to stick with you for the entire life. So if you are to like what you have to evaluate yourself against like what was not the new knowledge that you gained after this course. So that's what is your proper evaluation for you. The scores are all just there for the test etc. and assignments etc. are just there for as a formal things like to grade people and to tell who is topping etc. But that is not the main criteria for attending any course. Knowledge you gain from the schools is what that will stay with you forever. So we hope that you are gaining good knowledge on this for at least at the like BTech level or B course or B course level. So yeah, thanks.
Anyways, with this, we'll sign out. Thank you. Bye.